G'day dudes and dudettes, Mr. Bennett here. What we're going to do today is just go through magnetic fields. Some of it will be revision of last year and some of it will hopefully be maybe new. Alright, so the first thing is magnetic field. We know we have a magnetic field when we have a current carrying wire, and we know that the magnetic field is going to be at right angles to that. So we can draw the field lines a little bit like this, and the direction of those field lines is going to be due to the right hand palm rule. So if you imagine wrapping your finger around that particular wire and doing that, the fingers tell you the direction of the current. So that means that they'll be coming out that way and they'll be going out that way. Alright, now obviously there's rings all the way along here. Alright, so easier way to represent that, as we learned about this last year, my current carrying wire here, is that we'll use the concept of an arrow. Alright, so an arrow has a pointy end and has like fins at the end. So that end's going to be like a cross, this end's going to be like a point. So if it's coming out, you'll see the points. So that's what we've got over here. We'll see our points over here and so on, and over here we'll see our crosses. Now obviously if you try and draw these equally spaced, then what that does, it tells you that that's a uniform of a magnetic field around there, and so that would be the direction for that to be going in that direction there with the current. Now the formula that we use is a thing called F equals BIL and sine theta. Now quite often sine theta is going to be equal to 1 because it's going to be at 90 degrees to what we're doing there. Now the other thing that you need to know is we're going to use the right hand palm rule, and I know some of you struggled with this a little bit last year. I'm going to try and draw a hand. Oh, that's terrible. But you know, for the purpose of what we're doing here, I think you'll get the idea. So there's my hand. Alright, so we know that here we have this thing going in this direction here, and they are field lines. And that, I mean, I think that should make sense. And then we've got this thing going in this direction over here, and that there is my current. And then over here, if you think about your palm, pushes outwards over here, and that's the force, because your force is going to come from the palm of your hand, and that's supposed to be all at right angles to each other. It doesn't look very good, but you get the idea. Okay, so I mean the main thing is to be able to use that. You don't have to draw that, you just have to predict where it's going to go. Alright, so an example might be something like, well, we've got our field lines here, and you know, by doing a nice regular grid, you're sort of saying it's a uniform field. We've got our current carrying wire going in this direction here, nice straight line. We've got a current going in this direction here. So if you're thinking about the current, now that's going to be going to the right. So you put your fingers pushing into the page, you put your thumb in the direction to the right, and that means that there must be a force that's pushing that upwards. So you're showing the direction of force. Now obviously if you show the direction of force, you don't need to state it, but you might say up the page. Now let's say this had a magnetic field of 2 Tesla. We have a 50 centimetre length of wire, and let's say the current over here is equal to 6 amps. Alright, so therefore, to work out what the force is on this thing over here is the force is equal to BIL. So that's going to be equal to 2 times with the current 6 times by 0.5, because that's got to be in metres, and that will give you a force of 6 newtons upwards. Alright, get the idea? So that's what we did last year. We did a fair bit of work with the right hand palm rule and current carrying wires inside magnetic fields. And obviously the application, I'll do a video up on the moving coil loudspeaker. That's the application you need to use, the concept of magnetic fields and current carrying wires. Now, we'll do one more of these just as an example for you. We could also draw field lines like this. Oh, nice straight lines. Geez, I'm drawing good today. And then we have our current carrying wire going in this direction here. Now, if it was going in the same direction as the field lines, there'd be no force, because there'd be... Alright, so it needs to be at right angles. It could be at an angle, but yeah, it doesn't often happen, but we'll do one, maybe do one of those. Alright, so here we've got a current carrying wire, and we've got our force over there. So your field lines mean your palm goes, or your fingers go to the right, your thumb goes upwards, which means it's going to be, the force is going to be into the page. Now just make sure that you learn how to do that, and if you need some help with that, please ask for some help. So again, we'll just do this one over here. Actually, no, we'll do another one of those very quickly. Right, so let's say we've got our current carrying wire at an angle this time. Right. And so let's say the angle there is 30 degrees. Right. And let's say we've got a current of 5 amps. And the magnetic field strength over here, B, is equal to 1 Tesla. And what else do we need to know? The length of the wire. Well, we don't need to know the length of the wire, but what we can say is the force per unit length is equal to BI sine theta. Okay, so the force per unit length is going to be equal to 1 times by 5 times by sine of 30. Now sine of 30 is equal to a half, so that's going to give you the force per unit length is going to be 2.5 newtons. Okay, and that's obviously the direction is going to be sort of into the page. It's going to be, it's not quite totally into the page, but it is sort of directed into the page. Generally, if it was a moving charge particle, it might actually spiral, and that's quite interesting when you look at things like that. Okay, so that's all the current carrying wires. Now, really what a current carrying wire is the electrons running through a piece of wire. Now, conventional current, we say, is a positive charge. Okay, so we can do the same thing here with current carrying wires as we can do it with charged particles. Now, classic experiment is we start looking at observing what happens to particles as they move through a magnetic field. Okay, and what happens is, depending on what the charge of the particle is. So what was observed is, when you put charged particles into a magnetic field, you could have some particles that do that. You could have some particles that go like that. Imagine that being a straight line. And you can have some charged particles that do that. Okay? Alright, so if we're thinking about our right hand palm, right fingers, our field lines are into the page. Conventional current, right, conventional current is positive charge. Okay, so that's the direction of a positive particle moving in that direction. So that means that the red one over here would have to be a positive charged particle. The blue one, because it doesn't actually move, means it's got no charge at all. And the black one, if you think about that, then it has to be a negatively charged particle. And we'll look at that in class if you are not quite sure about that. Alright, so that tells us that we can have charged particles also moving in magnetic fields, and they will actually move rather than having to restrict the electrons or the charged particle to a wire. Okay, which is an important concept when we start looking at how we're going to use these things in lots of devices for physics. Alright, so I'll leave the video here today. We're going to be talking about, in our next video, we're going to be talking about the charged particles, and I'll show you some little derivations of the formula from the one that we're using today.